extremely happy to have Russ here, who is a professor in the machine learning department. Russ has very famous research projects that you all have heard about, like autoencoders, Boltzmann machines, here's neighbor encodings, which I like very much, and tons of other things. What he's going to talk about today, from what I understand, is structural memory for reinforcement learning. So far, our policies, our actors and critics have been taken as input a single frame, 2, 3 frames, 4 frames, and Russ is going to show us methods that take long-term, that construct a long-term memory of the scene, and this is much beyond LSTM. This is going to be akin to a geometric map of the scene from what I understand. So this is very exciting and enables, yes, much larger capabilities on the navigation domain in particular. So they should feel free to ask questions.
Oh, yeah, feel free to ask questions.
Ask questions so that you feel you understand the material.
Yeah,
Thank you, Russ, for this. Thank you for coming.
Absolutely. So if you have questions as I go through the talk, just ask me questions. So I'm going to talk to the whole lecture is going to be kind of like dedicated towards the use of memory. In the last couple of, last 3 or 4 years, people started exploring the notion of external memory. And I'm going to show you some examples of that. Let's see if that works. Okay, so I'll give you a little bit of a background. I'll probably go over background quite quickly, just because this is a reinforcement learning class, so you probably know a lot about reinforcement learning by now. Then I'm going to talk about neural map, which is location-aware memory. And then I'll show you some examples of how you can incorporate prior knowledge within memory, particularly in the language domain, which is a very different domain from reinforcement learning. Okay, so we all know that a lot of deep learning algorithms basically stated as a supervised learning problems, right? You're basically mapping inputs to the outputs. And in this setting, the environments are typically static. The outputs are assumed to be IID or independent of each other, which is a standard setting. But in reality, when we look at the environments in the reinforcement learning, the environments can be dynamic. They can change over time. Actions that you're taking in the environment can affect the environment with arbitrary time lags, right? So the action that you take right now could have an impact on the environment long-term into the future. And it's also the case that labels can be very expensive or difficult to get, right? And this is why we typically rely on reinforcement learning to learn complex behaviors. And just very quickly, instead of providing a label, the agent basically is provided with a reward signal. High reward encourages good behavior. And reinforcement learning will produce policies. You're mapping observations to actions. And you're trying to maximize some long-term reward. And it also allows us to learn some interesting behaviors in dynamic environments. Okay? So, for the rest of the lecture, we're going to assume that we're going to be using deep neural network that's going to be parameterizing our policy. Right? And we can adapt parameters of our policy by using Q-learning, actor critic, evolution strategies, a whole bunch of different algorithms that you can do, right? And this, I guess in this class, you've covered a whole bunch of those already. Let me show you one particular example, which is the example of a navigational task. And here's an example of basically navigating in a 3D environment. This is a little bit of an older paper, but it shows you the input is basically frames. These are pixels. The actions are turn left, turn right, go forward. And the rewards here are basically collecting objects. So you're not telling the environment how to navigate. You're just basically telling it, do whatever you need to do to collect as many objects as possible. And what's interesting about this is that, through the process of learning, you basically able to navigate in these complex environments.
The input here is just a single perspective.
Just a single frame, yes. So the single frame, and you just have you just output the action, and so it avoids things like going into the lava. You can train with random textures. These are kind of like 3D navigational tasks in a simulated world. But what's interesting is that once you train with a whole bunch of different textures, then if I put the agent in a new environment, unknown environment, a new map, then the agent can basically navigate in this environment without any problems, right? So basically now I throw it in an unknown map and it basically moves around, right? So that's interesting. Now,
So this new map has new textures also.
yes, this new map has new textures, so it's kind of like.
In the randomization, you start training that how wide trial was this? How many textures?
So I think that at the training time, is a good question. I think at the training time there were over 20 different textures. Right, so it basically learned to figure out like there are things that's, corners and walls and sort of some geometric, I guess, notion about the environment, but it's, it's able to navigate in the environment pretty reasonably well. Now, the problem with what I've shown you so far is that these are the systems where you're learning so-called reactive policies, meaning that I observe the frame, I take an action. I observe the frame, I take an action, and I instantly forget whatever I've seen so far, right? There is no notion of memory, there is no notion of planning, there is no notion of just basically just executing. Here's what I see, I take an action. This is what next I see, I take an action, okay? So can we learn an agent with a more advanced external memory? And in 2014, there was an excellent paper coming out from Alex Graves called Neural Turing Machines, which was a combination of a bunch of previous works, but which basically sort of put together this notion of external memory. And these excellent papers to look at. The idea is you're basically designing the external memory mechanism where you can write to this external memory and you can read from this external memory, okay? And one of the key challenges, which still is the case, is that memory systems are very difficult to train, especially using reinforcement learning objectives, which are very noisy, unstable, and so forth. So I'm going to show you some examples in trying to solve this problem, but it still remains a very challenging problem. Now, why is memory challenging? So here's an example. It's a very simple example, but sort of illustrates why this is a challenging task. So suppose an agent sits in a simple random maze, okay? So you see the agent over here, this guy, and somewhere near the start of the state, the agent sees an indicator, right? And the color of the indicator basically determines which goal the agent has to navigate to, either here or here. So for example, if it's a green indicator, I have to navigate to this goal. If it's a blue indicator, I have to navigate to this other goal. Okay? So why is this challenging? Well, if I tell my system a priori these rules, if I tell the system, if you see green, go to this target. If you see blue, go to this other target, then it's an easy problem, right? But it becomes a difficult problem if I don't tell the agent anything, right? The agent goes in the 3D world, does a bunch of exploration, random actions, hits this target, gets positive reward. So the reinforcement learning algorithm will basically say, okay, well, that was a good set of actions. Go to this target next time, right? Next time you hit the same target here, you get negative reward, right? And so through the process of exploration, you start figuring out, well, I keep hitting these targets, randomly placed in random mazes. Sometimes I get positive reward, sometimes I get negative reward. What's going on, right? And eventually you have to figure out that there is this indicator that tells you where you should go, right? Now the challenge is that the time that it takes you to travel from seeing the indicator to the goal could be arbitrarily large, right? And that's where the problems come in, because standard systems like LSTMs and recurrent networks and such, they're not very good at maintaining or storing the information over long periods of time, right? So you need something beyond that. So this is just a very simplistic task, but you can make it arbitrarily hard for any reinforcement learning algorithm that uses LSTMs or just does evolution of the recurrent state will fail. So you need something beyond that, and you need some mechanism to store things. One particular way of doing it would be to store everything you see, right? You get the agent and you just store every single frame. And then you try to do some kind of retrieval mechanism to figure out like what have you seen and how it correlates with where I need to go. So that would be a very inefficient way of doing it, but that's one way of doing it.
To ask you something.
Sure.
So this task, which is simple, but it's not to us, to humans, it's not intuitive. It doesn't have objects, it doesn't monsters to kill, etc.
That's right.
How long will it take us to understand that green should go to red? And
yeah, it's basically through the process. I'll go through the model that does this, but it's through the process of learning. Very inefficient right now. Oh, humans can solve this particular task fairly quickly.
So they understand.
They understand that if you navigate in some 3D environment, you're seeing these objects, and very quickly, with like a few iterations, you start picking up correlations, right? Now, this problem can be made arbitrarily large because I could have this environment, and I could say, you know, if my laser pointer points this way, you have to exit through this door. If it points this way, you have to exit through this door. Figure this out. Now, obviously, it would be impossible for humans to figure it out, right? So you can obviously make it arbitrarily hard, right? So there needs to be some prior knowledge that you can incorporate, for sure. Yeah. Yeah. Question?
So how about just to record every frame for the situation that's surprised the agent?
You have to, yeah, so then you have to define what the surprise means.
Like
Right.
the uncertainty.
Sure, but then these are random mazes. So every episode, you get a random maze, right? Now, you can make it harder by basically saying walls will have textures. There would be some things on the walls, and then certain indicators. Yes, you can do that, but then you have to define what the surprise is to store what you need to store. So at the start, there is no prior knowledge. But then the following has to hold, right? You have to write the color to the memory somewhere at the start of the maze. You have to never overwrite memory of the color over t time steps while you're doing exploration. So you have to maintain this indicator. And you have to find and you have to enter the goal, right? Otherwise, you get negative reward. And one solution would be to write everything into the memory, which is not as efficient, but nevertheless is a solution. Okay? So now, before I get into the model, I'd like to spend a little bit of time talking about the basic idea of memory and the basic idea behind neural Turing machines. It's an excellent paper. You should read it. The basic idea of neural Turing machines is you basically turn neural networks into differentiable computers. And you're doing it by giving them a read and write access to external memory, right? So the idea is that what you're effectively doing is you creating these neural networks that separate computation from memory. And that's a wonderful idea, I think. That's sort of like, there's a bunch of different papers that were put together around the same time, you know, attention for machine translation and so forth. And then these ideas were kind of like put together into one paper, and it's a wonderful paper. I think that the insight again here is that you're separating compute, what your neural networks are doing, from memory, what you're writing and what you're reading from the memory. And I think that's a very important idea, and it's a very important contribution, because so far, when you look at a lot of practical applications like ImageNet classification or any tasks, in lots of the settings, your neural network essentially stores information about the data, right? When you're trying to classify dogs versus cats, your neural network kind of learns the right sort of representations through the training data to figure out how to classify things. But these are quite different because these systems actually allow you to store something in the memory and read something from the memory. And the nice way that it was done is that you can define differentiable compute, which basically means that you can learn what you need to write, where you need to write, and you can learn what you need to read at what time. Okay? So here's the architecture that was introduced in that paper. So the idea here is the same. You have external input and you have external output. So you're still mapping inputs to the outputs, right? Except for now, you have so-called controller, and you can think of a controller as a neural network or recurrent network or feed-forward network. It's a controller, and you have two heads. You have read head that reads something from the memory, and you have a write head that writes into the memory. And you can think of a memory as just a real valued matrix. Okay? And everything here is differentiable. That's important because that allows you to develop algorithms that basically allow you to learn what you need to write into the memory, right? What information you need to write into the memory.
So, Russ, what is the most exciting part about this memory? Is it the fact that we don't need to all the memory to be powered up at every iteration if we do hard attention, so that this memory can be huge? And I should not waste computation because,
so it's,
or even if it's soft attention, still is exciting because in comparison to RNNs, these are more permanent and they don't change.
So the as we'll see in the rest of the lecture, so they've defined so-called soft attention, which is kind of like a distributed read and distributed write. It's still better than RNNs in some sense because you can permanently store something over long time steps. People will also try to do hard attention, which is kind of like, use some kind of reinforced algorithm to figure out what to write at one particular location. I'll show some examples of that. But again, these systems are extremely hard to train.
So what you're saying is that this memory is better at preserving values as opposed to these forget gates of LSTMs.
That's right. They're much better to preserve values over long time steps, for sure. So let me... Right, so let me tell you how these things are implemented. And it's actually pretty easy. Yes, question?
So when is the memory accessed?
So the controller decides what to access from the memory.
How does it decide?
Oh, I'm going to show you. Yeah. So I'm going to show you how these operations are working right now. Right? And then we're going to go through the neural map, which will make it much more precise exactly how these operations are done and how the whole thing is differentiable. Okay? You first look at this and like, how in the world can you decide this to be differentiable? It's hard. How do you decide what to write, what to read, and so forth? But it turns out that the solution is actually pretty simple. One of the things that we need to do is we need to have a notion of selective attention. So we need a notion of attention mechanism. So what we need to do is we want to focus on the parts of the memory where the networks will read from and write to. So you need an attention model. And what we're going to do is we're going to use outputs of the controller. So think of it output as a neural network to parameterize the distribution over the rows of the memory matrix. Okay, and I'm going to make it precise what that means. And this particular weightnik will define content-based attention mechanism. Right. So it's almost like I'm going to give you a query vector, or the output of a controller going to be some vector, and I'm going to define an attention mechanism that chooses the location in the memory. And then I can choose to write into that location or read from that location. Okay. So how do we do addressing? Well, we're going to be doing addressing by content. So we're going to have a key vector k, which is going to be output, which is going to be the output of the controller, and it's going to be compared to the content of each memory location. So think of a memory as a matrix. You're going to be comparing it to every single row of this matrix. Each row is going to be, think of it as like a cell in the memory. Okay? And we're going to be comparing using some similarity measure, S. So typically those would be cosine similarity measures. And then we're going to be normalizing it with a softmax. So it's almost like saying, it's a soft way of saying, given the vector k, find me locations in the memory that are as close as possible to my vector k. Right? So you can think of it as almost like a retrieval mechanism, or identifying which part of the memory you want to either read from or write to. Okay? And let me show you what exactly we're going to do. This is what these weights would look like. So given k, which the controller outputs, think of it as a neural network, outputs k, a vector of dimension k, or k vector, I'm going to be using some kind of similarity, cosine similarity. I'm going to be comparing it to a particular address in the memory. Again, it's just a vector using cosine similarity. And then I'm going to be normalizing it over all rows of the memory, right? And then there is also typically parameter sharpness, beta. You can think of it as a temperature that can tell you like how much focused you want to be versus how much spread you want to be, right? Do you want to concentrate just on a few cells locations, or do you want to spread it out? And here you should note that this is where the expensive piece comes from, because you have to sum over all memory locations, right? And this is why it's called soft attention, because these weights are giving you probability distribution over all the rows in the memory matrix. And this can be very expensive, because if your memory grows, you have to kind of, compute this. And the reason why we need to do this softmax, this normalization, is because we're later going to see that the whole thing then becomes differentiable. In fact, when we look what the read operation does, the read operation will return a vector r, which is the read vector, as an input to the control at the next time step, so that you're reading from the memory and you're giving it to control at the next time step, and it's just going to be the weighted average, right? So it's almost like taking an expectation of the memory with respect to these weights, right? Yeah.
And Russ, this beta is produced by the controller, or it's a fixed parameter?
It's a fixed parameter. I think
does
in the
it
paper,
change during training? We make it
yeah,
like
so it's kind of like, initially you can make it be sort of, I guess, large, and then you kind of like force it to be small. It's a hyperparameter that you have to play with, right? And so now your read vector is just the weighted average of the memory locations, right? And you can make it as sharp, or you can make it as wide as possible. And again, the reason why, you can think of this as an expectation operation, right? And one thing you should know is that, if you want to find a derivative of some discontinuous function, if you take an expectation, the whole thing becomes continuous, which means you can differentiate. So that's why these are sometimes called soft attention mechanisms, is because I can actually take gradients with respect to parameters over here. If I had to choose a single location, if I had to sample from the softmax, I would basically say, choose the maximum. If I said I'm only going to be looking at one location, if it's a sampling operation, then you could potentially use reinforce, right? Because you're only choosing one, so it's almost like you're taking action. But the problem then becomes that the training becomes far more unstable. So it's a trade-off between efficiency versus optimization efficiency. And then each write head receives an erase vector E. Think of it as just some vector, maybe zeros, or I think they learned it as well. And you basically add it into the controller, and then you write it to modify the memory cell. So now you're updating the memory by basically saying, here's what the content I want to update my memory with, and this is how much do I want to forget what I've written to the content of the cell before, right? So these are very simple operations, but at the same time, they are differentiable, right? And for example, here's what they can do. Here's a copy algorithm. They've trained it. So here you're looking at the time. So I'm just giving you a bunch of inputs that you can see on top. So these are the inputs. And I wanted the outputs to be exactly the same thing as what the inputs are, right? So what they learned is that they basically learned this is what you're storing in the memory. And this is your weighting, right, or your W's. And W's become very concentrated at a particular location. So it basically says at this location store this vector, this location store this vector, and so forth. And then the model learns that once you need to output, it basically goes to this location, retrieves from the memory what the thing is, and outputs it, right?
This is trained under which loss?
This is trained to just reconstruction loss.
Of the full output.
Of the full. So training basically contains these inputs, these outputs. So it basically tells them, well, figure out what you need to do so that, given these are the inputs and these are the outputs. And it basically learned to just store, right? It sort of says, if you have a memory, big matrix, eventually the weights would say the first one, this location, store this vector. Second location, this location, store it, and so forth. They've also shown that, you can do things like, if you're only training on like 10 inputs, 10 outputs, so you're just learning to 10, go from 10 to 10 inputs to 10 outputs, they can actually generalize to almost 120. So, they can generalize to this algorithm to basically say, I'll store more information and then recover it. Once they go to 120, there are some errors that start popping up. So there you can't perfectly store it, but it's actually pretty good, right?
And I want to ask you, when do you start applying law? So you let it, let's say, think, right? Or some
I think
steps, and then...
Right, so the way that they do is that, it's like a sequential thing, which is like x1, x2, x3 that comes in.
Mm-hmm.
And then at each time you're basically writing, you're learning what to write. And then at output time, you're just reading. So at the input time, you're writing, at the output, you're just reading. But I think that in their case, the algorithm basically learned the weighting, it learned that it just basically needs to store and then just copy it from the memory. So it basically learned to store and then copy from the memory, which is kind of nice.
And the controller takes the memory as input, right?
That's right. That's right. The controller takes the memory as the input, yes. They could also do things like copy n times. So they basically saying, well, if these are my inputs, I need to copy these inputs n times, right? So essentially, they just basically say that store it, and these are the weights, into the memory, and then at the output, you just you start with this content, you read it, again you read it, and so forth. So they basically showed a bunch of examples that they can learn things like for loops, for example, and these are differentiable for loops. They've learned things like iteration to step, variable count to n, and so forth. So they can count for a whole bunch of things. Obviously, these are standard operations, but it was interesting that they were able to learn non-trivial things. Like learning a for loop is just by examples, right? You're not telling it, this is a for loop, you need to do it n times. I just give you inputs, outputs, input, outputs, and you have to figure out that it's actually a for loop. Now, at the same time, still, the training of these systems is fairly brittle, so it takes a while to train them, right? So, now, one thing that, coming back to our problem, let's say the navigation problem, one thing that you can do is you can say, well, what I'm going to do is I'm just going to store, let's say I'm going to store in key in value or just the frames, representations for the last m frames. So I can just say I have a buffer of m things, and I'm just going to store in what I've seen in the past m frames. And then what I can do is at each step, I'm going to be performing a read operation over the memory database. And the read operation is nothing more than I just observe the current thing, I extract its features from the frame, let's say, I look at the cosine similarity. Here's my thing that comes in. I'm basically looking at cosine similarity between what I have in my memory. I create the probability distribution, and then I'm reading it from the memory. There is a sort of like a special way of something called key value, which is keys used to compute this probability distribution, which basically says where I need to look, and the value is what I need to retrieve. So sometimes people do, break it down into two pieces. And these memory networks have been used quite successfully in language tasks, for question answering tasks. So your memory could be you're storing a bunch of sentences, and then I give you a query, and I look at the closest sentences in my database. I retrieve the closest ones, and then I can ask questions about documents, for example, right? So these systems have been used quite successfully in language understanding. But here you can also do the same thing. You can just store m frames.
So which part now is easier with the memory networks? The fact that when you say store representation for the last 10 frames, you don't need to learn that.
That's
you
right,
just store.
that's right, that's right. So the only thing what these memory networks are doing is that they avoid the problem of learning what to write.
So
They just basically just write everything. So the write operation is fixed, basically. And it's only read operation, which is you find similar things and you do the retrieval. So it's almost like a differentiable retrieval operation. And that makes the problem much easier because you actually don't need to learn what to write. You write everything, right? And writing is actually pretty challenging task because it's a distributed write and so it's generally quite difficult to get to work. So it's easy to learn. You basically store as much as possible, but it can be inefficient, right? So you need M, whatever you're storing, to be larger than the horizon of the task you're trying to accomplish, right? It's almost like when you're born, somebody sticks camera on your forehead and you record your entire life, right? If you could do that, fine. But at the same time, can you learn something more intelligent? Can you learn something like things that you don't need to store? Can you learn to store things that are important for you to take actions in the future, right? That bring you the most reward, for example. And time and space requirements basically increase with M. And so even in the space of like language understanding, question answering, what people typically do is they say, well, I can't store every single Wikipedia thing. What I'm going to do is I'm just going to do some simple retrieval, find maybe 10 articles, and then like store all the sentences and do this attention and such. So let's look at the neural map, which is a very simple extension of the memory network, which basically takes the following inductive bias. So we're going to be structuring memory into W by W grid of k-dimensional cells. Okay, so you have a cube, k by k. You have to define, it's W by W. And for every location xy, you write into x prime, y prime in a W by W grid, right? So here you're making one fundamental assumption, which is you know the location of the agent. So if you're here, you're writing in this part of the memory. If you're here, you're writing in this part of the memory. Here, you're writing in this part of the memory, right? So here you're making an assumption. I'm going to show you some examples where we can relax this assumption, but the key assumption is that we know where we are. So what we're going to be doing here is we're not going to be doing distributed write, but we're going to be doing location-specific write operation, which substantially improves the stability of algorithm, right? But it comes with an additional prior knowledge that we have to know the location, right? This is like there is no free lunch. So whatever we do, we have to put either some kind of prior knowledge or something. And so basically it acts as a map of the agent, fills out as it explores the environment. Okay? And so the inductive bias here prevents the agent from overwriting its memory too often, and it can learn whether it needs to overwrite a particular location or it actually learns whether it actually needs to store what it sees in the environment. In many cases, basically doesn't store. Eventually, it learns to store these indicators, right, into the memory, or the state of the indicator into the memory. So how does it work? Essentially, you can think of it as, you have some state, you get some features from the state, you write into a specific part of the memory, you take an action. Then, given an action, the environment gives you the next state. You read from the memory what you need to read here, so that becomes part of the feature here. And then again, you update your memory, and so forth, right? And so that persists through time. So if you look at it, it actually looks a lot like, kind of like an LSTM, right? But except for your hidden state now is a very structured hidden state. And you know exactly where you need to write in this structured memory, right? Which makes the problem much easier, particularly for the credit assignment problem, right?
And we read and write in different locations, of course. We can read.
That's right, that's right. That's right. So you read and write from the different locations. You write at the location where you are, but when you get to the target, I'll show you some examples, when you get to the target, the read operation actually reads from the part of the memory that has the indicator. So it can read the state of the indicator and then force the policy to either take an action to get to the goal state or, retract.
Memory access, is it by content? So you need to... Do you see what I mean?
Yes,
so to
yes,
retrieve
yes.
the indicator, you need to remember the color of the indicator to do the soft attention, or?
Yeah, so the way that it functions is that once I get to the state where I see the goal state, it basically learns that when I see the goal state, you do retrieval by content, but it learns to retrieve from part of the memory that has the indicator, right? So it basically learns to transfer like colors to the colors of the indicator. So it basically says, what I'm seeing right now is the target that I need to enter. The similarity of this target is the similarity to the indicator and nowhere else. And then once I retrieve the state of the indicator, then the color of the indicator tells me, do I need to hit this target or do I need to go back and find a different target, right? I guess.
So when you're learning, do you end up backpropagating through all of the states from the beginning of the episode?
Yes, we have to backpropagate. So we've used like versions of like truncated backprop. There's a little bit of curriculum learning, but yes, you have to backpropagate through the whole thing. Right now, the problem we've made it artificially hard because the only reward signals you get is if you hit the target, and that can be very large, right? At the same time, we're working in these kind of like 2D, 3D environments that are not too complex, right? But I think that ultimately to make it more realistic, you have to do some form of reward shaping, or you have to have some auxiliary things that you need to incorporate. Because sometimes the time when you hit the target and the time you observe the indicator and then random maze can be very long because the agent has to explore this environment. And so the reward signal is extremely sparse, right? So in this case, we made the problem perhaps too artificially hard for us. But at the same time, I'm going to show you with enough compute, you can learn this.
Do you write everything like before? Each time at every location, you see something, you just write it.
That's right.
Is this what?
That's right. That's exactly what's going on. This is more of a like I see something, I use convolutional. I'm going to show you exactly what the operations are actually. But it's yes, you write everything.
So the reading you're saying is hard.
That's right.
I see. And an engineering question. Let's say the map is this. Is this pre-allocated, or you assume you know what is the size of the map and where you start? Probably, right? Because we know where the agent is.
Yeah. So we know approximately the size of the map.
All right. Okay.
Right. So we kind of like basically say that if the agent has a particular location, it maps it to this part of the memory. Yeah. So I'm going to show some examples how to avoid this in an egocentric environment where the agent doesn't know the map and just moves around and explores. But then you have to solve like localization and stuff like that, which is also hard. Yes?
So when you're saying you only read some parts of the memory, do you just put the whole memory like into a neural network and then only some parts of it get out?
Yeah, so let me show you exactly what the operation is. It's like a soft read operation that I've shown you kind of like what neural Turing machines are doing. But let me go through the operations. So the whole thing is done through a bunch of operations. The important operations are the read, then getting the context, you're writing, updating the states of the memory, and then basically producing the policy. Okay? So let me go through all of these operations, and all of these operations are differentiable, which basically means that if you're using actor-critic, or if you're using Q-learning, whatever the target is, you can backpropagate through these things. So the read operations, there is two read operations. There is a global read, which is just the global summarization of the entire memory, and there is a context-based retrieval, which is, depending on what you're seeing right now, you're trying to retrieve that. We also have sparse write with only agent positions, and then we're basically using read and write vectors that we get. Basically, those are used to compute the policy. So there are a whole bunch of things you could do. There are a whole bunch of architectural choices you made, like do you really need the global summarization? Do you need the context-based summarization? Do you need both read and write to compute the policy and so forth? There's a bunch of things you could probably do better. But let me show you what we've done. So you're reading the entire, so the global read is just very simple. You're basically reading the entire neural map using a deep convolutional neural network, right? Because it's just a three-dimensional cube. You just do 3D convolutions, and that basically gives you some notion of what's stored in your entire memory, right? So for example, you can retrieve things like, oh, the indicator or the state of the indicator, or you can retrieve, the location of the map or the structure of the map that you've discovered so far, or you can retrieve pieces where you've been in the map, where you haven't been in the map. That can help you explore the environment more efficiently. Then there is context-based read operation. So this is sometimes called read operation with attention. And you have sort of bunch of equations here. And let me actually show you pictorially what these things are doing. Okay? So imagine that given the state that I'm currently in, so think of it as the frame that I'm receiving, what I'm seeing right now, the read vector, which is the global summary of my memory, initially just a bunch of zeros, but as I'm dating the map, it gives me some features. I now compute the query vector Q. Okay? So I'm just concatenating those two, pass it through another matrix W, and I get some vector Q. And let's say that my memory is just a 2x2 memory. Okay? What I do is I basically do a dot product between my query vector and every memory cell, right? So if I do the dot product, let's see if my animation works, right? And I renormalize, I get these probabilities alphas. So these probabilities alphas is basically telling me this entry is most similar to my query vector, right? So it produces a similarity alphas, which sum to 1. It's just a probability distribution over my memory. And then I basically take element-wise product between the query similarities and the memory cells, right? So it's just a dot product, element-wise product. And then I do the sum, which essentially kind of takes expectation. Given what I see, it's an expectation over the contents of the memory. The intuition you should have here is that you're basically returning the context vector C sub t in the memory M, which is closest to the query vector Q. That's what you're doing. You're basically saying, given my query, find me the closest vector in my memory, right? Except for I'm doing it in a differentiable way, right? Because when you're taking an expectation, if I have some context C, I can backpropagate through this entire thing, right? So I can update, let's say, the parameters of this thing. I can backpropagate through the read vector. I can backpropagate through, I can update what these things are and so forth, right? So this is essentially attention mechanism. Oh, sorry. Yeah, this is essentially attention mechanism, right? Differentiable attention mechanism. Yes.
What is the implication of taking expectation versus just taking the maximum of the alpha?
So you can take the maximum of alpha and backpropagate through that. It becomes a little bit tricky because you're basically going to hit some local optimum. What people have explored before also is instead of taking the maximum, you're basically sampling according to these alphas. So you sample from a probability distribution. In expectation, you basically will point to this cell, right? But sampling, then you can do it with sampling, but then you have to be able to. Anytime you sample, it's a discrete choice you're making. And if you're making a discrete choice, you can backpropagate through that discrete choice, right? You can use reinforce type of algorithm, which basically says sample a bunch of things and kind of average by backpropping through. You can do that, but then the variance becomes large, right? On the other hand, if you don't sample and your memory is like 1,000 by 1,000 or 1,000,000 by 1,000,000, and if your memory is 1,000,000 by 1,000,000, then you have to access every time you're reading from the memory, you have to access every single location of the memory, which is very inefficient. And so then there's like a bunch of follow-up papers that basically use some form of a hierarchy or multi-scale type of representation, right? So you can try to avoid that. There's still research, basically. Do you sample? Do you use softmax? Or do you use expectation? But the thing about expectation is that, again, you can backprop through it. You can just compute the gradients. So, but it's inefficient. And that's generally the case between soft attention, which is what you see here, versus hard attention, which is you sample from the alphas. Taking the maximum, you can do that, but it generally like extremely sensitive to, because you're learning what these things are. And so it's extremely hard to get it to work if you're just taking the maximum. Because effectively have to learn, you're learning what these vectors are. These are not given to you. If these were given to you, then yes. But you're actually learning what the content of the memory is. And so for the writing piece, you just basically, sure.
If we were taking the argmax, what type of gradient estimator would we be using? A reinforced type, I would say.
Yeah, it would be like a reinforced type.
Right. So the expectation is just a soft version of the argmax, like
Exactly.
softmax, and
Exactly.
differentiable basically.
Exactly.
But with computation, which is
Exactly.
what
Yeah,
we do
exactly.
now.
That's exactly right.
Right.
It's instead of reinforced would be argmax versus softmax, which is just the expectation. Yeah. So for the neural map, basically, you can also update the content of the memory. And you can update the content of the memory if you're in a particular location. You're just basically saying, well, if you're updating this part of the memory, you're just updating it. And the update itself could be, what we've seen before, right? It's just writing what I need to write. You can also do things like gating mechanisms. So the gating mechanism will effectively tell you how much of the memory I need to update, and do I need to update it at all, right? Essentially, the model basically learns that it stores some information about the map because it helps it navigate around more efficiently, but it doesn't need to store or it doesn't need to write it all over the place. If it was in the same location, it doesn't need to overwrite it. So essentially learns a sensible gating mechanism, basically says, most of the time, you don't need to write anything into the memory. The only caveat here is that it's a very structured writing, right? It's writing at just one particular location, right? And then the output, basically you have read vectors, you have write vectors, and then you basically just concatenate all of these vectors together. And you pass it through some nonlinearity f and through the softmax, and that gives you the distribution of reactions. Okay? And that's a policy. And now, given the policy, the thing about these operations that given the policy, if I take the gradient of this policy with respect to all the parameters that are sitting within these operations, you can backprop through them, right? So which is kind of nice. You have fairly, a set of complex things you kind of like doing, and you can just flow the gradients through the policy, right? So if you're using, for example, actor-critic, policy gradients, or any type of RL algorithm, you can compute the gradients of pi, right? So let's see. So let's look at some examples. So this is what the input state looks like. It's a partially observed state in the 2D environment, right? This is what you're seeing. And this is what the observed map looks like. And then here's an example of the agent moving in this environment. This is just a 3D visualization of the 2D maze. And so it's a random maze. It goes to the wrong target. It sees the wrong target. It backtracks, right? And it explores the map up until it finds the right target. So what's happening here is that when the agent was here, And so this target, it was able to correctly retrieve from the memory the state of the indicator and then take the action of go back.
Because if it would hit the red, it would be
Yeah, because if it would hit the red, you would get negative reward. But if the state of the indicator was a different color, then if it would hit the red, it would get positive reward, right? So essentially it learns to kind of like, and notice that the time that it takes to find it, because it's a random maze, there's a bunch of different mazes that we've tried. For longer mazes, you can basically fail your standard RNN-based approaches. Here's another example. Let me just see if it works. This is kind of like the indicator, and it sees the wrong target. It moves around the target, so it makes sure that it doesn't hit the target. And it moves around, and it's pretty hard, right? I mean, it's pretty crappy environment, actually, but it eventually hits the right target, right? It's kind of funny because these are Doom environments. They're easy to train with. It's easy to simulate. But at the same time, they're so hard because you look at the images, it's just a bunch of walls and there's nothing around them. So it's very hard to localize and move around and such. So we kind of like, when we were doing this work, we kind of like we're shooting ourselves in the foot because the environment is artificially hard and the task is hard. And then the reviewers are basically saying, this is a simple environment, why are you doing this? Right? Because in more realistic environment, I think things would have been a little bit easier. Just because the walls and everything looks kind of the same. But there are a bunch of things that you can do. You can also do some tasks where you're exploring the target. Once you find the target, you can come back to the original point where you started from, and so forth. So there's a bunch of different tasks you can do with the memory. You can also do, for example, you can obtain a map which is egocentric. So the agent always writes to the center of the map, and then the agent moves, the entire map moves around you. Right? So in this case, you don't really need to know the size of the map. You can keep writing, but it also assumes you have perfect odometry. Right? If you move 90 degrees to the right, you're making sure, you have to. So there are some caveats to this as to how much, as you're navigating environment and the observations are imperfect and your location is not perfect and such, you need to be able to localize and do these other things. So here we just didn't worry about those problems.
Russ, what about GPU memory? Did you have the problem of how to allocate? I suppose where you start the map and you start building and it gets very big. Eventually it's not going to fit, right?
Yeah, that's right. So you have to, so the memory itself, so you can think of it that the memory itself is, we basically discretize the map, right? And so the memory itself is a function of how, what the discretization is, right? And then in our case, no, yeah. I think that once you go to the continuous space, then it becomes much trickier. And this is where, because the memory is inherently discrete notion, right? If you want to store. If you go to the continuous space where the agent just continuously takes actions, you need to have some kind of a mechanism of either mapping the current position to some location in the memory. So you need to have some mechanism of doing that. So, yeah. So there are a few challenges. Here. But the thing that I wanted to point out about this particular thing is that it helped us substantially to put this inductive bias when we're writing in just one specific location, as opposed to doing distributed writing. Kind of like writing everywhere in the memory and reading everywhere from the memory, which I think is far more unstable. Now, let me show you one other example very quickly, which is incorporating some price into language tasks. And so there's a lot of work happening in the language domain where people are trying to say, well, how do I, given some textual representation, how do I basically take some notion of the prior knowledge that I know about the language and improve my representation of a recurrent neural network? Okay. Well, here's one way of doing this. So suppose that I give you these sentences. Mary got the football, she went to the kitchen, she left the ball there. And if I ask you the question, where's the ball? Obviously it would be in the kitchen, right? Turns out that for machines, it's quite difficult to get that reasoning Because you have to know something about Mary. She's carrying the bowl, she's going to the kitchen. Kitchen is some physical location. She's actually placed the bowl like there. And so now if I ask you where's the bowl, you have to associate that it's in the kitchen. It's not like you can look at one sentence and answer the question, right? So it requires some form of, or at least a little bit of reasoning. You can build an RNN, which is what people typically do. You just basically have some hidden state and you pass it forward and such. And then I ask you, where is the ball? You sort of like say, well, ball, I'm seeing the ball here. I'm looking some context around here. Maybe I can answer the question. But you can also use things like co-references. So whenever I say she, I really mean Mary, right? It's not like some other person. And I also know that football and ball, they mean the same thing, right? It's the prior knowledge that I can, put into the system. Because if I ask you, if I don't have this prior knowledge and I don't know that football and ball mean the same thing, if I ask you the question, where's the football? I don't know, like Mary has the football, right? So there's no football appearing anywhere else. So I need sort of this kind of knowledge. And there is a way of kind of constructing a memory mechanism where you basically have these additional links that you can put into the structure of the recurrent network. And you can basically have an update equations, there's standard update equations for recurrent neural networks, but with these additional links. And there's a specific way of incorporating those things to make it fairly efficient, and you can ask and answer questions, more complex questions about the task. So people in the language domain are also trying to incorporate some notion of memory, either through the prior knowledge. It's almost like specifying, I need to store in my memory these things. So when I'm incorporating them into the RNN hidden state, I can actually read it from the memory, right? And so, ultimately, how can you build agents that can have external memory, that can reason and communicate with you, right? So there's a lot of work and people trying to basically figure out, can I build an external memory? Can I build some knowledge base? Can I get my agent, to communicate and such? And maybe just in the last 5 minutes, let me show you one example of something that's called language grounding task. So in the language grounding task, I give you a sentence, such as go to the short torch, right? And your agent has to figure out what that means, and it has to go to the short red torch, okay? And you can train it using reinforcement learning. Basically, this is the first attempt we've tried doing it. It's very inefficient. It's more like, I give you this sentence, I convert it into a bunch of numbers. Given those numbers, I condition those numbers to my policy, and my policy has to find the red torch. So through the process of learning, basically policy just stumbles around, and then eventually it starts figuring out what is red, what is short, what is torch, right? So here's some examples of like 30 minutes of training and doesn't really know what it's doing because it has to explore the environment to figure out what that thing is. But then eventually it sort of like figures out things like, it's spinning, go to the tall red pillar or go to the green torch. Go to the blue short object. So then things like, for example, tall or short or smallest is pretty difficult to describe, right? And so go to the smallest blue object, right? And then there's like, there are certain proper test instructions. Like, for example, you've never seen a blue short key at the training time. And at the test time, you're telling it, go to the short blue key. So it understands blue, it understands key, and it understands short, but it's never seen this combination at the training time. And it's still able to figure out how to put these things together to navigate to the right target. So these are sometimes called language grounding because to really understand the meaning of the word short, it's pretty difficult to describe. Right? And there are sort of some examples that I think Devendra's done, which is basically you have an environment and you say go to the smallest object. You go to the smallest object. You take this object, you take it out of the room, and you say go to the smallest object, and it figures out how to go to the next smallest object. Right? So of course these are very kind of like constrained environments. Ideally, you'd like to scale it to thousands of instructions with thousands of different concepts. And the architecture here is kind of, at the high level, it's fairly simple. You sort of process your language instruction using a particular recurrent neural network. You process your visual input through the convolutional network. There is certain gated attention mechanisms that allow you to attend to the relevant parts of the language and the relevant parts of the input representation, and then you're basically outputting the policy. And the policy tells you what action you need to take, right? And there is a whole bunch of work now on visual question answering or embodied question answering, where you have some agent in the environment and you're telling the agent what is the color of the table. So the agent has to figure out where's the table, has to navigate to the table, figure out what the color is, right? So stuff like that, which is fairly challenging tasks, right? And finally, the last other thing that I wanted to show you is this notion of localization. I think so. Localization is, in my view, is also a very important problem, right? If I throw you in some environment, and let's say I know the map of the environment, your goal is to actively localize. And active here basically means that you have to take a set of actions to localize as fast as possible, right? Which is very different from kind of like passive localization, where I show you a bunch of sequences, and then you have to tell me where you are in the map. Here, you basically have to design an algorithm basically telling you, find me the optimal sequence of actions so I can localize as fast as possible, right? And so we've been looking at some examples of where the agent basically, here you're looking at the belief of where the agent is, and here's the ground truth. And so after a few settings, it basically localizes itself. So, it's not perfect, but what effectively it learns to do in these environments, basically learns to do like a 360-degree spin. That's the most informative thing to do, at least initially, to figure out where you are, right? And so it's basically then just a few more steps, and it figures out the relative positions of the walls and such, and it knows where it is. This was done using Unreal Engine. In fact, we found that localizing in a Doom environment is way harder than localizing in this environment, right? Because the Doom environment, basically everything looks the same. You have no idea where you are. Here, in like an office scenes or a few outdoor scenes, so here's the I guess it's localization in the Doom environment, but
Russ, how does the map look like? Does it have deep features or is just this image?
we have deep features.
So it's like the previous map where you were writing the deep features, right?
That's right. That's right. So there are a few things that we've done here, yeah, and then there is a belief over the state where we're maintaining the probability distribution of where we are, right? And then we backpropagate, so we also have a transition model. Transition model, basically, if I take a particular action, there are 4 different maps where I am, and like if I'm facing north, and I'm facing east and stuff like that. So there's a bunch of different things that you can do. But here we're also backpropping through, so we're finding the right representations, the right features to do this localization. And hopefully that will also take us towards looking at a problem known as a simultaneous localization and mapping, or SLAM, where we can try to identify differentiable versions of the SLAM. So we can learn how to solve SLAM, perhaps using or active SLAM, where I have to take actions to figure out how do I build a map and how do I localize in the map. But that turns out to be a far harder problem than just localization itself. Okay, so just to discuss, let me just quickly say, well, can we extend these examples to the multi-agent domains, right? Multi-mail agents basically communicating through the shared memory. Okay, so if I have a couple of agents, how can they explore the map more efficiently, right? Obviously, one agent would explore one part of the map, the other agent would explore another part of the map, and as soon as one agent would find the indicator through the shared memory, they could both find the right target. So we've sort of tried working on this. It's kind of funny. We sort of started hitting local optimum. And the local optimum is basically we have 2 agents, And the agents, they have LSTM hidden states as well. They have a shared memory. But what happens at the training is as soon as one agent finds the indicator, it stays at that location, right? So it has these features of the indicator and just communicates to the other agent the states of its hidden state. So it basically says, forget about the memory, right? As soon as I find the indicator, I'm going to stay where I am while the other agent explores and tries to find the right target. So that's a suboptimal behavior, because the optimal behavior would be to write into the joint memory and continue exploring, right? So we sort of find these interesting examples where the optimization finds these other ways of solving the problem. So here can we train an agent to learn how to simultaneously localize and map the environment? And so that solves the problem of needing an oracle to supply XY position. So if we could actually have localization mapping, we could start building our neural map and start learning what we need to write and what we need to read from. And then we also were thinking about structuring these neural maps into multi-scale hierarchy, right? So that each scale can incorporate longer range information. This is particularly if you start exploring the environments that are much larger, right? As opposed to, and so this is where these examples of kind of like a multi-scale memory or multi-scale read or write operations can come into place, or can come into play. One final thing that I wanted to mention is that I think that this idea of memory and the idea of separating compute from what you need to store is a pretty significant idea. I don't think these kinds of memory mechanisms have been very successful so far. And I think the reason why is because we just don't have the right algorithms to train them efficiently, right? What ends up happening right now, at least in practice, is that people say, well, if I make my LSTM state be bigger, right? Or larger, or have multiple maps, multiple hidden states, looking at different scales. And that seems to, solve, some of the problems that we're trying to solve, right? So that's what's happening. That's what's happening right now. But at the same time, you can always break those algorithms by basically saying, if what you need to store, can take very long periods of times, pretty much any existing algorithm will fail, unless you have something that you can actually store. Like, copy n times. If I say copy it 1,000,000 times, without having a memory, there's no way you could do it. Any sort of RNN, LSTM will fail. So, yeah.
I'd like to ask a question on SLAM. So this active localization says that you are allowed to choose your actions to localize yourself faster. Do you think if we have active agents for SLAM will be a much simpler problem? Instead of us collecting data, humans, and then give them to an algorithm?
Yeah, so that's one of the things that I think that it's ultimately, you probably want to have an active SLAM agent, right? You want an agent that takes in actions to figure out how to build the map as efficient as possible, right? So I think in terms of efficiency, it will be faster, as opposed to us providing the agent, the algorithm, okay, well, here's the path you need to take, collect some data offline and then try to do SLAM, which is what a lot of, I guess, traditional robotics algorithms are doing. The issue with active SLAM, in my view, is that to train these systems, you need some environment, right? You either need some virtual environment that looks realistic compared to the real environment, because what these agents are doing is they basically saying, well, if I take this action, would I localize or would I build a SLAM faster, right? And so you need this notion of and it's hard to do it in practice, because if I have a robot, I better just, collect the data using a sensible set of actions, as opposed to getting the agent to just explore. Because there's an exploration. Yeah, and unfortunately there aren't a lot of good simulators for this task. Yeah.
I want to ask, would you consider using traditional SLAM methods within this active loop instead of making a neural and end-to-end differentiable? Because in any case it's not differentiable.
Yes. You can definitely. There are, some of the things that we've tried doing is we basically took the SLAM architectures, traditional SLAM architecture like graphs and such, and just try to make them try to make them be differentiable.
Right, but we don't need to because it's reinforcement learning.
Yeah. So, but the thing is, it's a reinforcement learning. But if my decision is to take an action, right? That's true. That's reinforcement learning. But if within this decision, somewhere inside, I also have to make a bunch of discrete decisions, then it becomes much harder problem. Do you see what I mean? It's almost like in a memory, because the policy itself produces a set of actions. So I say go forward, turn left. But when I compute the policy, the entire policy is differentiable. But if I had to do hard attention for the reading, for example, or the writing, then I would have to make some discrete choices inside my policy.
Right.
And
For example, now I'm taking a
yeah,
step and I need to see how my point cloud is going to match.
that's right.
And then I have 2 steps, I have different memory. So it's harder.
It's harder. Yeah.
It's worth checking though, right?
Yeah, I agree. It's worth checking it out. I don't think well, we've looked at some robotics literature. I mean, robotics literature,
They don't have active SLAM.
they don't have active SLAM, yeah. But I think a lot of it is because you need a simulator or you need
To
something
learn
to
and
explore and to learn and such. It's very difficult to do active SLAM in the real world, right? Yeah. Yeah. Any other questions?
I have one more question with the language grounding. Since the reward was, I reward you if you reach the right object, correct?
Yes.
Why don't, this means that I know who is the tall green
Yes.
torch. Why don't I train supervise the attribute classifiers for objects? Then I learn the
Yes,
object
you
classifier.
can totally do that. You can put a bunch of auxiliary losses and have like a supervised classifier that basically says, or even detectors. You can just say, here's a blue torch detector. Right, you can definitely incorporate that as an auxiliary tasks. You can definitely, and that's something that I think Devendra is doing right now, and it helps a lot in terms of the speed of learning. In fact, you can take off-the-shelf detectors, put it into the system, right, and it can start learning things like if I have a table detector, it can start understanding there's something that's called a blue table or red table, and sort of like association with other attributes and such, for sure. Yeah. That's a good way of incorporating prior knowledge into these, for sure. Yeah. I have sort of students who, core RL students that basically say we can solve everything from ground up. But obviously to make it more realistic and in practice, you definitely need to put the prior knowledge, you need to put auxiliary losses and such. You definitely do know that this is a torch and this is a green, and this is a red, because at the training time you have that data. So definitely you can use it as auxiliary loss, and it will help speed up the training considerably. Yes. Yes.
The torch one, that, for example, if we have 2 red small torch, and you ask the agent to go to the small red torch, but assume we have 2. And the one is far from me, and the other one is near from me. So I would think the further one looks smaller, so I would go there. But after I approach the smaller one, the further one, when I look back, I think the other one is smaller. So will the agent go back and first course because we are 2 same?
Yeah, so the agent basically learns to explore. So if you have 2 torches, 2 red torches, and this looks small to me, this looks larger to me, the agent, through the process of training, learns that it basically sees this thing. If it thinks this is small, it navigates to this one.
Yeah.
And if it sees this is bigger, it comes back to the original one. Right.
I mean, the 2 red torch are actually of same height.
Oh, if they're of the same height.
Yeah.
If they're of the same height, then the model just has to find one of them.
But I mean, the one is far from me. It seems like it's smaller.
It
So
learns.
I
No, but
approach
it learns not to make those mistakes.
Oh.
Right? Because it's not so. This would be a problem if I couldn't move. If I said, here's a fixed frame, which one is the smaller torch? Then I would be confused, this smaller, this smaller. But because what I can do is I can move, I can this, I can come closer to it, then I can find the relative things. And here, when we look at the small, we had like small, medium, large, so it wasn't like they were different by like 1 millimeter, so you really had to figure out which one is smaller. Like you could identify one is smaller than another, but because you take actions, you can disambiguate. And I think that's why working with settings where the agent can take an action is pretty important. Because if I'm confused about like who's including what and how far things are, I can just like move here and then move back, and I can disambiguate that. Yeah.
So how far do you think we are than having those robots out there to run these navigation RL algorithms that are being trained?
Oh, I don't know. I don't know.
We don't know. Maybe not. I was wondering, maybe you know because you are in Apple. Who knows what's happening?
Right. Yeah, it's gonna take a while. I think that it's. There's another question.
Yeah, I was wondering, what do you think are the major roadblocks to getting these kinds of methods to work in real-world applications?
Ooh, so I think that when you think about like incorporating memory, right? I think that the main roadblocks is just the training algorithms. They're extremely inefficient. So, for example, to solve the simple task of navigating to the right target takes like a few days on multiple GPUs, and it's a fairly simplistic environment. So that basically means that we either have to have better auxiliary losses, reward shaping, and so as I mentioned before, I think that the notion of memory is a pretty important one because it can store things over arbitrary long time periods. But learning these models is extremely difficult. And so that's why most of the successful applications of memory is like memory networks in language. It's basically you store everything. You don't learn what to write. You just store everything and then you just do retrieval, differentiable retrieval mechanism. As soon as you start figuring out what information you need to write and how this information will impact your actions long-term into the future, that's an extremely difficult thing to do, right? Humans are pretty good at doing this, right? Mm-hmm. You put I had a friend who put like money on Facebook, and the Facebook just collapsed. And so he learned not to do that, right? And so, you basically, I think that humans are pretty good at somehow remembering things in the past. And generalizing them, that's right, and generalizing them very well. Like this is one situation, here's a completely different situation, but it's generalizable to this new situation, right? And so, yeah, there was a question?
Just an amusing thought, like hyperparameter tuning for reinforcement learning is also kind of a reinforcement learning task. So I'm wondering, you can use this neural map to store store network architecture.
So there is a work right now, I believe, like in the last couple of years, people are using reinforcement learning to do hyperparameter optimization. They like just actions, you're choosing the parameters and so forth. The issue there is it's extremely unstable and difficult to design the policy. And if you do design the policy, you want this policy to be generalizable across different data sets. Right, ideally. Here's the data set, here's a policy that produces the hyperparameters, but
You remember that this one architecture works, you store it in the memory later.
I mean, that's what people do most of the time, right?
Okay.
Like, yeah, sure, but it's still, I can tell you that, what's the most important hyperparameter? Learning rate. Your learning rate should be 0.01 or 0.001, period. Works about 90% of the time. Right.
Other questions for us?
Yeah.
Yeah, so you mentioned that getting better simulators is like an easy way to sort of improve fix the problem. Do you think just better simulators or improving the training algorithms is going to be more important?
I definitely think improving the training algorithms. And I definitely think improving generalization, like Trina was saying. Because what you want to do is that it's almost like we need like an ImageNet for RL, where you try to solve a bunch of different tasks and you try to generalize across different tasks. I think we definitely need better algorithms. If you think about this, supervised learning is hard, but we sort of been successful at solving it. Reinforcement learning is not as hard as unsupervised learning, but it's still hard because your rewards are sparse. And as I mentioned, like with the addition of the memory, it's just we don't have good algorithms right now. I think this idea of separating, again, compute from the memory is a fundamental idea that people will be exploring in the future. It's just that right now we don't have good way of learning these, On the other hand, if you're watching like OpenAI, they had a game of Dota, which is a fairly sophisticated game. You have 5 players, and people thought that you need some notion of. I thought you need some notion of memory, you need some notion of planning, you need some notion of strategy. And well, turns out if you just big gigantic LSTM, kind of works. So you never know how far you can push existing algorithms, right? So maybe you need just more compute. And so.
But what if this is the wrong evaluation of algorithms? What if the right evaluation is what Schema Networks did that says, give me your algorithm, I'm going to change tiny bit the environment, and let's see how well your algorithm works.
Yes, exactly.
So maybe our evaluation is wrong.
Yes, I agree. Yeah, that's a fair point.
Thank you very much, Russ.
Cool. Well, thank you.